Thank you. It's a really pleasure to be here. Thank you, Andrea, for a very nice and very nice introduction. It's actually interesting because when you're saying about it, I mean, it's definitely true. My passion is advancement of women faculty, but in generally, really advancement for underrepresented minority and minority groups in academia. And that really started with Linda Fried. And I don't know how many of you know this story, but I was and just recently promoted associate professor at Johns Hopkins, and Linda was at that time the director of the Center of Aging and Health at Johns Hopkins. And I knew of her. I didn't collaborate with her, just I knew that, she was one of the very few, very prestigious women in medicine. And one day, she called me and she said, well, I am leading a university-wide task force on advancement of women at Hopkins. Do you want to be the co-chair with me? And I was so honored that Linda asked me. I was like, yes, sure, we'll do it together, yes. And that started really 2 years of incredible adventure working with Linda. And that was actually throughout my pregnancy as well. I was very pregnant at that time. So as a result of the experience, and then I'm going to go back my talk, but as a result of my experience, I learned a ton from Linda, and we wrote actually a paper and published in Academe. It's called Why So Many Few Women Leaders. And that was how I got the award at Johns Hopkins from the president. So all of this to say that you have the right role model here, and really she had a big impact on me, and she still has. All right, so yes, I'm going to talk about hopefully all topics that are interest to you. And I made this talk a little bit flexible and I'm going to try to figure out based on the audience how I'm going to focus more in some areas on other. And also wanted to say that this is joint work with a lot of colleagues and friends. And I wanted to highlight that Zhao Wu is one of your incoming assistant professor in the Department of Biostatistics. And you will see that a lot I'm going to talk about is actually Zhao work. So you're really lucky to have him. So let me first start with some key points. I like to start with that. So then if you want to just take a break, because some things I do, it's fine. So I always think about environmental and climate policy from a very heavy data science viewpoint. And I think that there are really some so for me, there is a data science viewpoint, and there is also an optimistic viewpoint. And I always feel in academia, we have to always be optimistic. So the good news that there is more data. There is a satellite data, atmospheric chemistry model, machine learning, artificial intelligence. They're really now transforming the way that we can measure things. And also in the context of environmental health, to measure exposures better with unprecedented precision. And then we are continuing to develop, and I'll talk about that a little bit, really state-of-the-art methodology in causal inference that allow to better understand health impact and also identify the most vulnerable. And then, the pandemic has raised the attention of public health issues and environmental health issues. And for all of the bad things that have been happening with the pandemic, I think it's as helping us increasing the sense of urgency for the work that we are doing. And I know here I'm preaching to the choir, but I'm a very strong advocate that data science really are one of the most important and effective tools for policy change. And this slide tells you all, right? I mean, the Cleaner Act is asking to, the Cleaner Act led to the EPA to mandate to lower the national ambient air quality standard for fine particulate matter when there is evidence that the current standards are not safe enough. And so when you have a policy that is based on data science, you have a positive results. You see that the levels of air pollution in the air have been declining over time. I don't think that they are still low enough, but definitely there has been a tremendous amount of progress. The other thing is, now there are all of the major university, Columbia's, climate school, Stanford has also climate school, and Hopkins, Harvard has I still confuse when I'm from Harvard or Hopkins. Sorry, sorry for the people that are online too. Anyway, Harvard, the Climate Institute, and sometimes people tell me like, oh, air pollution is different, right? No, it's the same problem. Climate change and greenhouse gases emission and air pollution share the same sources. So if we are very active in regulating air pollution, not only we're breathing better air tomorrow, I think is a good thing, but we're also targeting the major causes of greenhouse gas emission. And so ultimately, all goes back to attacking fossil fuel combustion, right? So it's really two manifestations of the same problem. Now, one of the questions I've been really focused in the last 2 or 3 years, and with a large team, is really, it was a very specific but highly impactful question, which was whether or not exposure to fine particulate matter, even when it's a level below the national ambient air quality standard, the long-term standard of 12 micrograms per cubic meter, is associated with a mortality risk. This is, we still haven't heard from the Environmental Protection Agency whether or not they're going to lower the national ambient air quality standard. Hopefully they will. I think we're getting closer and closer. I'll tell you why. But this has been really the question that I've been focusing. And so this is a question of trillions of US dollars. Okay, so the Clean Air Act benefits ranging from 1.9 trillion to 3.8 trillion in 2020, and 2.5 trillion to 5 trillion in 2030. And that doesn't account, this is just for health benefit from breathing PM 2.5. It does not account for if they're lowering from 12 to 5, like the WHO has done, means all of the climate change benefit, and we call it the co-benefit, because it will immediately reduce and target fossil fuel combustion. So as you can imagine, this was a slightly controversial question. And the type of research to provide the answer to that question has been led to a tremendous amount of scrutiny. And so I'll tell you a little bit about my journey when I was stressing this question. So first of all, there is no good data science, there is no good evidence without good data. And so I've been really focusing part of my entire career on building research data platform. I'm the strongest advocate, and I think it's also very important as for the more senior faculty and the more leadership to really focusing on this issue, because you need a tremendous amount of resources, and you also need to hire data science and data engineers that can work on the data research platform for a very long time. And so basically, it's a research laboratory designed to learn about itself. We continue to add the new information and new data. So it's growing organically. So information about exposure to environmental contaminants, risk factors, and then how to help. And so to tell you a little bit more, and many of you have been working on this data and interacting with us, and as well as sharing the frustration of not getting the clean data soon enough, because it's a really major undertaking. So we have all of the Medicare participants, it's over 67 million people from 2000 to 2016. Actually, we just bought 2018. This is a cohort. So every time someone turns 65 years old, they enter in Medicare. So they are in the cohort, and then we can follow them over time, and we know their date of cause-specific hospitalization or mortality. So we can track all-cause mortality and any cause-specific hospitalization. We have limited information at the individual level, unfortunately. We have the date of death, we have age of entry, year of entry, sex, race, and whether, this is a very important variable, whether they're eligible for Medicaid, and being eligible for Medicaid is a proxy for lower socioeconomic status. And then because we have the zip code of residence, we have all of the census information, right, available at the zip code. So this is the hardest and time-consuming and expensive thing to do, to have a scalable and rigorous data platform, which none of us is trained to do that. And this is not work that should be delegated to a PhD student or to a postdoctoral fellow. And that's where what I mean, like, it's a lot of resources and time. It's the harmonization and integration of heterogeneous sources of data. And there is a tremendous amount of actual intellectual input. So slowly over time, and with the, and by the way, this is also where the NIH doesn't pay, right? But I've been assembling a data science team and a data engineer that is working on all of this harmonization that sometimes can be different depending on the study that you're doing. If you look at health effect on power plants emission, you require a different level of data integration of space and time than if you're doing a study on climate change or hurricanes or on air pollution. So the research data platform really has an element which is we are continuing to work on it in measuring, assembling, and integrating exposure to environmental agents, all of the primary pollutants, chemical component of pollutants, climate stressor, of course, temperature, humidity. Robbie has been enriching the data platform, thinking about exposure to hurricanes and tropical cyclones. And then there is a team is enriching the platform from Stanford with exposure to wildfires, right? Different teams. And this is also really where this is a complex problem that we all need to work all together, right? So different teams from different parts of the US, not only at Harvard, are refining their model for measuring exposures, and we are trying to integrate it into this data platform where we can, figure out a way of sharing the data in a way that people get the credits. And then it's linked to the health data. The health data is really the part that it's sitting at Harvard, but we have data user agreement. So also we have a data user agreement, I was talking to some of your colleagues, with Columbia. So you can access the Medicare data because of R1 and Robbie's K and Marianti. So fortunately, John cannot take our VUA to UW, but that's okay. We still love you. And so we have been harmonizing all of this data together. So let me spend a little bit of time on artificial intelligence and machine learning model for exposure assessment, for air pollution exposure assessment. I was not the lead of this work, but this is like one area where data science, I think, has been making tremendous progress, and there is a really very exciting area. So if you're looking at exposure to air pollution, this is the map in the United States where you see the monitors where we measure daily level of fine particulate matter in the air. So you see that it's monitored pretty well, but still it's not monitored everywhere. And remember, the health data is available everywhere. So there has been a tremendous big area of research, and actually your colleague Marianti is leading an R1 on this topic, which is developing machine learning model and actually ensemble learning models to better estimate exposure to air pollution. And under the field of computer science and machine learning, actually, this is really a very interesting and explosive area of research. It is very little about machine learning for spatial temporal data, right? And that's really an area where really Marianti is very much involved. The general idea here is that you take satellite images and more specifically aerosol optical depth, that is an imprecise measure of air pollution. Then you take output of atmospheric chemistry model, and then you train this neural network model and get an estimate of PM 2.5. Of course, when you think about ensemble learning, what's happening is that there are several different machine learning models that different teams have been developing. And so there are new methodology that can combine, so then you can improve the accuracy. There is all a topic about that. What I'm going to just point out here is thanks to this methodology and the improving methodology that we're having, we are now can measure exposure to all the primary pollutants at 1 kilometer grid daily for all the continental United States. So not only that, but one thing that's really exciting to a colleague of mine at Harvard, they actually now can also measure the different chemical components of fine particulate matter. This paper is under review. at really, this is, I think, done a 1 kilometer grid, right? So it's really hyper local. So you can see actually there is a map here of New York, and this is elemental carbon. So you can see the degree of which we can track at daily level these chemical components. So this is really a collaboration there also with Amazon Web Services and Microsoft Azure, because you can imagine that doing machine learning and prediction for this type of spatial temporal data for over 20 years is something really incredible. So I'm just going to give you like two little chapters in terms of, okay, from really now my biostatistician data science hat, what has been our story in terms of estimating health impact of PM 2.5 throughout the last few years during the pandemic and transitioning from the Trump administration to the Biden administration. So what everybody does when you try to estimate health effects of air pollution and generally health effects of environmental contaminant, you all know this, you either apply a Cox proportional as a model if your outcome is time to that, or if you want to be more computationally efficient, you can think about the equivalent of a Poisson regression. So the first paper on this topic was in 2017, where this was a very impactful paper because it was for the first time where we published a national study linking air pollution, PM 2.5, and all-cause mortality for the whole Medicare population. So 97% of the population older than 75. And again, the question here was also not only whether or not long-term exposure of PM 2.5 increase mortality risk. We kind of already knew that. But the policy question was, well, does the PM 2.5 a level below 12 micrograms per cubic meter, so below the safety standard, increase mortality risk? So the population here is huge because we were able to study 32 million Medicare enrollees that breathe what's supposed to be safe level of pollution. And then we have 247 million person years, right? So this, actually, remember in 2017, we ran this analysis on Christmas Eve on all of the Harvard supercomputer. It was the only time we could have all of the computing power for all Harvard. And it's interesting because 2017 was 6 years ago. Now we can run the same analysis in just 15 minutes, right? So this is right, the incredible of how quickly on Amazon Web Service Cloud, right? So it's really interesting how quickly we adapt. So what we found, so this was a Cox proportional as a model, and we found that overall for the whole population, a 10 microgram per cubic meter increase in PM 2.5 led to a 7% increase in all-cause mortality. What was really, and again, this was before the pandemic, and we found that African American experienced mortality risk, which was 3 times higher than the national average. And also we reported, and I'll tell you more about that, even for the people actually that were breathing cleaner air, so a level of PM 2.5 below 12 micrograms per cubic meter, actually the mortality risk was even higher. So again, before pandemic, this had a big splash over the news. And again, this was at the time where we were in the Trump administration before COVID, really trying to criticize the study, not to implement and not to lead to regulatory policy. Now, these were all of the good voices. Senator Cory Booker actually used our study not to appoint a Trump supporter at the Environmental Protection Agency. So there is actually a very interesting video if you want to look at on the website. This was one of my glory days. It's just like every time NIH rejected my grant, I just watch that video. So you all have to do what you have to do, right? So, but that was a good day because he cited our study and asked this woman, which was pushed by Trump, whether or not she thought that there was environmental inequity in the burden of PM 2.5, and she had absolutely no clue. And so he said we should be tested. Anyway, so this was all of the good, but this was the bad, right? So Steve Malloy, he was a Trump appointee, really trying trying to dismiss the study. There was I was accused of scientific misconduct. This is like there is this website if you want to have some fun. It's called junkscience.com. And he accused the editor-in-chief of the New England Journal of Medicine and myself and all of the author of this paper of scientific misconduct. And that was at the time where the chair of the Clean Act Advisory Board of the EPA was Tony Cox. So basically discrediting all of this work. The interesting thing is that the reason why they were discrediting all of this was that we use standard regression models, and we couldn't show that there was evidence of causality. And so that's where, I mean, this was in 2017. And it's like, well, but there is this huge field of causal inference methodology. And, why don't we use that? So we basically started to really think about, and it started from before, to really further develop a causal inference methodology for estimating an exposure response function. And so to be able to be responsive to that criticism, which, by the way, that's now become a huge thing. If you're interested in terms of causality in the context of air quality policy, we just published a new report of the National Academy of Science. Actually, Kiros Bahrain, who is the chair of Biostatistics here, was one of the members of the committee. And so there is really now much more attention and recognition that not the method for causal inference to give you the bulletproof of showing, things work or not, but it's important to think about the rigor of thinking about causal inference because it does increase the scientific rigor. So what's causal inference, right? And so I'm just going to use one slide, and then I have more technical stuff, which I don't know how much I'm going to go through it, but I do think sometime, especially for this type, when I'm giving a seminar, my goal is to give you the fundamental idea of why it's powerful, and then you can always read papers and get the software. But really, the fundamental idea of causal inference, I also appreciate it in the context of matching or exact matching. And so let me give you like a very simple example. There is actually this paper I wrote with Corey Ziegler that is very digestible, easy to read, guidance of using ideas of causality in air pollution epidemiology. And I can tell you now that we have this report out, I think that, having a policy impact, this is something that I think you need to be aware. But it is very simple. So let's say that you have 2 geographical regions in the United States. Super simple. Portage, Wisconsin. By the way, I picked these from the famous 6 city studies at Harvard. Like there were 6 cities, right? So Portage, Wisconsin is a city has a low level of air pollution, and Swinville, Ohio is a place that has very high level of air pollution. What's the problem with all of the air pollution study? Okay, so this is I'm going very basic. Well, first of all, we cannot do a randomized study, right? I cannot randomize a group of people and say, you just go for the next 20 years and breathe bad air, and you just go there. We can't, right? So it's an observation. So because in an observational study, the mix of the population is going to be different, right? You're going to have some percentage of people that, so for example, in Portage, Wisconsin, you're going to have a larger number of people that have a higher socioeconomic status and so on, right? So you have to adjust for this difference. So then you say, okay, what's the big deal? I can just fit a regression model and I can put a covariate and adjust for these differences. Yes, you can, but by doing so, you have to assume that your regression model is correct, right? If your regression model is incorrect, then once you're going to adjust for the difference, it's not going to make a difference. It's going to make a big difference. You're going to get the bias estimates. So the idea, it's really simple, is to think about a counterfactual. What's a counterfactual? So let's say that I have one observation, and let's say I'm interested in Jane. Jane is a high school teacher. She's 53. She's been living in Swinville, Ohio. I know her body mass index. I know her diet. I know that she had a history of cardiovascular disease. I know a lot about Jane. And I also know that Jane died at 85 years old. Okay. The goal is I wanted to know if Jane, how much longer Jane would have lived if Jane would have lived in Portage and breathed less pollution for her life? Okay, this is really the question I want to know the counterfactual. How many more years Jane would have lived if instead of being in Swindale, which she would have lived in Portage? Well, of course, I will never be able to do that perfectly. However, if I have Medicare data, or if I have a ton of data, I can find in Portage all of the twin sisters of Jane. I can find all of the women, they're 53, same body mass index, same education status. I can find a lot of matches, a lot of twin sisters of Jane, where the only difference with respect to Jane, or the of course it's not going to be perfect, would be that they breathe with pollution, right? And so if among these matches, on average, they live up to 92, I'm going to say that there'd be an extra 20 years due to breathing better pollution. This is the fundamental idea of causal inference, right? Then there are 1,000 papers of different approaches in perspective, but this is the idea, okay? And so this is an excellent book by Guido Immens, which, by the way, was a Nobel Prize winner of economics last year, with Don Rubin on introducing the idea of propensity score. Now, the idea of propensity score is the following. Instead of matching with respect to all of the measure coefficients, you can match based on the propensity score, which is the propensity of getting a higher pollution level versus not. So what we did now in 2020, we took the entire database, so we updated the database up to 2016, and then we developed new methodology and we applied the same methodology for causal inference to address the same question. So this was work actually led by Zhao, so you can ask him all about it, and my colleague Danielle Brown, who's a senior research scientist. So was it the same database, just more people, because we updated to 2016, and now we have 38 million individuals that are living, they are breathing level below 12 microgram per cubic meter. So remember that harmonization, integration of different data sources. Also interesting to see that the level of pollution has been going down from the level of pollution in 2000, and this is in 2016. So you can see actually that we have clean up the air quite a bit. The question is whether or not levels below 12 are important. One very important piece of causal inference is the ability to address for confounding, and whether or not there is confounding in a very simplistic manner, whether or not there is a correlation really between your potential confounder and your exposure, which is PM2.5. And you can see that NO2, humidity, percentage of Black people, temperature, right? These are all of these variables that have higher correlation with PM2.5, and these are tracked to the validity of making causal inference, some causal inference conclusion. So we analyzed this giant database, not only using the traditional approaches, but then thinking about new approaches for causal inference. So the matching approach is a new approach for matching when you are estimating a causal exposure response function, so in the context of a continuous exposure. And that paper has been just published in JASA 2 weeks ago, and there's a software package. I'll give you the reference. And then we also use existing weighting approach and some general adjustment approach where you put a propensity score into the regression model. I'm just going to skip this. And so just to give you an idea that one slide in terms, right? So there is the code here, and the idea is basically now I wanted to estimate an exposure response function. So my exposure is not binary; it's continuous, right? In the context of continuous exposure to pollution, but could be continuous exposure to temperature or anything that you are interested. And you want to estimate an exposure response function that has a causal interpretation. And so what it means is basically you have to find the matches in the same way I gave you the example with Jane, but instead of only for 2 geographical regions, a 2 value of exposure, for every value of exposure throughout the entire exposure response function. So basically is to create a new data set that approximates the randomized experiment as much as possible. And so you wanted to jointly match on both of the exposure level, but also on the generalized propensity score. And so the fundamental idea is really that you go from the original observational study into a new data set where for every individual, you know their generalized propensity score and you know their exposure, and then you find all of their twin sisters and twin brothers, right? So it's going to be a matrix, right? That you're going to have N is the number of people and L would be the number of matches, and then you're going to find your potential outcome. So it's just a much more, bigger computational issue, but the fundamental idea that I gave you with Swindle, Ohio, and with Portage, Wisconsin, and Maine. But the very important thing, and one nice feature of the causal inference methodology is the fact that you can look at covariant balance. You can, when you have created this new match data set, you can look at the data and say, am I approximating a randomized experiment good enough? Up to a certain level. Remember that one of the fundamental assumptions that I should have said sooner is that there's no unmeasured confounding, right? You could have many unmeasured confounders, and then all of this is not going to help you anyway. But if you're measuring, you're thinking that you don't have many unmeasured confounders, then we can have a different discussion about measured confounding. But among the measured confounders, you can see that the red dots are the observed correlation in the data set, and the green dots are the correlation in this new match data set, right? And so the bottom line is, if you can match really well and you're breaking the correlation between the exposure of interest and the potential confounders, among the measured confounding, you are really very effective at adjusting for confounding bias. And so this is a paper in Science Advance, and all of the code and the exposure data is available. But basically what we did to inform the policy was we ran the analysis both using standard regression method and causal inference method that you can see actually for the entire cohort. The standard regression method were pretty much aligned with the causal inference methodology. For what was very interesting, and by the way, this is a result that has been consistent through 2 other teams, a team in Canada and team in Europe, is that actually when you restrict the analysis for people that are breathing cleaner air, a level below 12 micrograms per cubic meter, actually the mortality risk is higher. So in fact, I'm going to show you the shape of the exposure response curve. And there you see the difference, right? That you see that for the people at low level of exposure, the causal inference methods give you an estimate is lower, but for sure positive and statistical significant. And then there is a lot of approaches that you would see in the JASA paper where we actually estimate the full exposure response function. And you can see that there is a steeper slope, a lower level compared to the higher level. Now, we have done a lot of additional refinement to this work. I'm not going to go into much of the details, but just to tell you, and you can find that on the archive, and hopefully it's the last stage of revision, to with my colleague to extend the work from a Bayesian framework. But the reason why we did the Bayesian framework is that you can estimate the confidence band of the exposure response function much better. But very importantly, you can calculate the posterior probability of whether or not there is a change point in the exposure response function. That for a regulatory question is it's very important. So I'm not going to go into all of the details. I'm just going to give you 2 slides, which is the fundamental idea. The fundamental idea is to remember that you have to model the potential outcome at each exposure level for each value of the confounders. And what we assume is that the potential outcome for each exposure level, the level of confounders, is given by this very flexible function f. And this flexible function f is a Gaussian process. And then when you have a Gaussian process, we baked in the matching procedure into the covariance function of the covariance. And so the idea is that the off-diagonal element of the covariance function have a distance between 2 units, and the distance of these 2 units, so two units, they have a closer propensity score, and a closer exposure will have a higher correlation, right? So it's the idea of taking the matching that you can do manually, but then take the matching into a distance function, that's going to be the off-diagonal element of a covariance matrix. So then, basically saying people that are more similar with respect to the propensity score and the exposure, that would be highly correlated. So, but what's nice about that, because we frame all of this within a Gaussian process, actually the potential outcome is a weighted average of observation or observed outcome, has a Gaussian process property. There is a lot of very nice mathematical property where you can calculate uncertainty, but also, which is very nice, and this is a simulation study, you can identify the change points, right? So I might just give you an example. This is a simulation study of an hypothetical exposure response curve, and purposely simulating in a way that there has like some change point. And then with the Gaussian process, the first derivative of a Gaussian process is also a Gaussian process. And the first derivative is what's going to tell you whether or not there is a change point. So through the simulation, here you see that there is a change point here, a change point here, a change point here, and so on. And so we were able to, the Gaussian process, to know where the change points and exposure response functions are. And that's critical because it tells you whether or not there is a change point on 10 or 3 or 5 or 12 microgram per cubic meter. That is really the policy question. So we apply to the same database. And so this is our result, that basically this is the exposure response function, right? And actually it's very interesting that currently this is a WHO safety standard for PM2.5. This is the current EPA for safety standard. And this is actually where we found the evidence of a threshold in the change of the exposure response function. And this is the Gaussian process as the first derivative. And you see that in this data set, we have almost zero correlation between exposure to PM2.5 and the covariance in terms of that we'll be able to adjust for confounding. So if you're interested in this work, there is actually the GitHub repo is here. There is a package. Actually, we are developing the package, and the paper is published in the archive, and hopefully it's going to go through all of the review process. And so I thought that I didn't go to all of the detail, but I found it very, I would say, comprehensive and elegant Bayesian approach for estimating a causal exposure response function, quantify the uncertainty, and identify the change point. Is it going to make a difference? We don't know yet. Hopefully, as I mentioned, the WHO has lowered the national metal quality standard from 12 to 5, and we're waiting the EPA decision now under the Biden administration. I wanted to finish up with a little bit of more into the climate and health. And so I wanted, of course, to give a shout out to Robbie and Marianti through the Medicare data and some of the work, and to other data as well as the National Center of Health Statistics. So this was a recent publication of them, and in close collaboration with Harvard, and really trying to not only thinking about health impact of air pollution, but also health impact of tropical cyclone with the county level mortality data. In this paper, Robbie used, I think, was the cause-specific mortality, but then he also has the cause-specific hospitalization and all-cause mortality with Medicare. And this is really interesting, has the power of this data platform is that allow to look at the short and long term, like few months after impact of exposure to tropical cyclones and hurricane on all different cause specific mortality. I think that the neuropsychiatric condition is something that we were talking about before. It's really very important, especially from hurricane, as well as infection and parasitic disease. And Rob is leading, I would say, very productive and comprehensive line of research on this field. The other great collaboration I want to mention is on heat, and I think this was also really important work by my colleague at BU that we did together. And this is looking at heat and risk of emergency department visit for mental health among US adults. And that's actually, they use a different data platform, they use a different health outcome in this context with the Optum database. And it was pretty interesting, if you think about here, they, for example, when they're looking at contrast of the 95 percentile of local warm season maximum daily temperature compared to the reference, they have up to 11% increase in childhood onset behavioral disorder. And this is the exposure response function of cumulative exposure response function between warm season temperature and emergency department visit for any mental condition. So we know, and we are documenting more and more, that extreme temperature is also a mental health problem. And then, among again, at the intersection of climate, air pollution, and COVID, this was, I think, a very impactful study, and hopefully it's definitely cited by the EPA multiple times, so that hopefully is going to lead to the lowers of the national ambient air quality standard for PM2.5. But this is where we studied the impact of exposure to wildfire to exacerbation of COVID, and especially COVID mortality when we had the 2020 wildfires season in the United States. So the 2020 was a really crazy year, because not only we were in the middle of the pandemic and before vaccination, but also there were multiple wildfires in the US. So basically we took daily data on exposure to wildfires and daily data to cases and deaths, and look at the relationship between exposure to wildfires and exacerbation of COVID, and we found a very strong statistical association. We had with a lot of attention from the press. Sorry, I misread the slide. I think we all learn, and we all learn all our lessons during the COVID-19 pandemic. So all of the good things have happened from a scientific viewpoint, and the things bad happened. And I personally pushed very much data transparency, and I would say transparent, impactful, and understandable data platform. So we built during the wildfires this platform where all the data are publicly available, the code is publicly available, and the idea is you can click in any of the. So we studied all of the available, where we have available data, counties in California, Oregon, and Washington State. And so you can click on a certain county. In this case, we clicked in Fresno. You can look at the daily COVID-19 cases. Here you have the ambient level of fine particulate matter in yellow, the levels of fine particulate matter that were attributable to the wildfires. We know the wildfires based on satellite. You can look at the level of PM2.5 on wildfire days and non-wildfire days, and then through our modeling, we estimated the attributable increase in COVID-19 cases, and that's due to these high peaks of PM2.5 that occurred during the wildfires. Of course, I basically gave you a very broad overview of everything going on. There is so much more that I didn't talk about, and so much more that we need to do, and a lot of the challenges. I think I just want to mention some of really great work on my colleagues are really thinking about causal inference for policy evaluation, thinking about multivariate outcome, thinking about exposure response function, and thinking also about this new machine learning method to really identify vulnerability as a series of concomitant factors. Reproducibility is something that we take really, really serious, but I also recognize that it's not easy. And we have Naeem as a member on our team, is a software engineers, and also like our reproducibility officer in terms of really encouraging to have a reproducible pipeline of how we analyze the data. Again, this is a really large group. It's actually these numbers are outdated. There's many more, but I wanted to really mention that this is a large consortium of people with PI from many institutions, including this one. And also the fact that we transitioned, on hybrid work has actually enabled really having more and more people involved. These are just a small number of the trainees involved, but there are many more. So just showing some pictures of some of the people involved and some of the people that you will recognize and hopefully to do more. So I'm just gonna wrap it up and say that the steps to mitigate climate change in the future are substantially the same as those who needed to reduce the burden of that disability to the air pollution in the present, which is to cut back on burning fossil fuel and biomass. And in the meantime, I think machine learning and data science are really promising venue to measure exposure and pinpoint susceptibility and vulnerability. And methods for causal inferences are not the magic solution to everything, but I do think have a lot of promises in terms of thinking about causality and assess assumption and look at covariant balance, and so to be a little bit less sensitive to strict model assumption. What I've been trying to do, and what my goal is, thinking forward, I really feel very strongly that the development of new research data platform is a priority. You can have the best possible statistical way to analyze the data, but if you don't have good data, you're in trouble. So, and as well as the linking of spatial temporal data, as we have this new technology available. And then again, as you're saying now, with a lot of great peer review publication, there is and more interest, and which I'm very pleased, and something I'm planning to do is really thinking about distribution of effect in the disadvantaged portion of the population. Thank you for your attention. I'm happy to take any questions.
So quick question is, does your group have any published papers on methods for this data linkage best practices? Because I actually think that's a huge issue. And it's often very unclear in people's written papers what they have done. So I think it would be, anyway, so if that hasn't been done, it potentially would be a really helpful paper to have.
I couldn't agree more. So no.
Okay.
I mean, just a simple question. So I mean, something I'm facing, like, so is it better? So is it better to do data to analysis at the zip code level or at the ZTCA level? So yeah, so no, but I agree with you. I think that would be very important, and it's not done.
Yeah, population centroid versus, anyway, there's like so many decisions people make without.
Well, the question is, though, we don't have the gold standard, right? So I think this is a challenge, is like when you say you can have a paper that lists all of the different ways to do it, but then unfortunately, the best way will depend also on the scientific question. And so I guess you will have to think about what the scientific question, but I think the challenge with that is, again, there's no gold standard, right? Yeah, but it's a need.
Yeah, no,
I do, but
Yeah.
all the other, no, that's okay.
thank you.
She's gonna tell me another paper I need to write. You have another 2 minutes to recover then.
Thanks very much, Francesca. Fantastic talk. And so I'm gonna ask one small question on Bayesian statistics. I'm very interested in that, but like from a regulatory perspective, is it, in your experience, have you found there's any pushback using Bayesian instead of regression? Because the first question I always get about Bayesian is, isn't it more subjective? And like, obviously, you have to explain that, but then is there a suspicion about it, or like, is there a learning that's got to happen with regulatory?
It used to be a huge issue. When I started in 1997, it was like, it was, you know, you're exactly right, but I don't see that anymore. I think, you know, the Bayesian analysis we did, it was just the machinery to be able to quantify the uncertainty, but I don't see that. I don't see that bias coming in anymore.
And then doing again.
Yeah. Thank you for a great presentation. I have a couple of questions on the chain point analysis that I guess maybe a little linked, so I'll ask them together. The first one is, do you think, I guess I would propose the underlying biological process is not a discrete change point function, but probably something more like a diminishing marginal effect. And so I'm wondering how the Bayesian model, you know, you say can detect the change point, but you know, if you look for a change point, you'll always find somewhere where you can best put it. And I'm wondering how the model deals with that. And then the second question, which is kind of the more the applied version, is it looks like the five parts per million that you're seeing is actually, you know, if that's the change point, that would actually suggest that the regulatory level should not be there. It should be somewhere way lower than there, right? Because that's where you're not going to get much more effect. And so I'm wondering how you think about that.
Yeah. So you are absolutely right in all fronts. So number one is, I mean, these models, they have the ability of being, you know, at the population level. We are not even trying to attempt to figure out what's happening at the individual physiological level. I mean, that's a different type of study, right? You're also absolutely right that it's not 5 where the level should be. The level should be 0 based on the exposure response function. The problem is that that's not attainable because there is always going to be a background level, and 5 is what is being argued to be the closer to the background level. I actually found that the analysis where we did to begin with, which is only looking at the cohort of people that were exposed a low level for the lifetime, and if you see a statistically significant effect among these people, to me that actually address the policy question better than estimating the change point from a statistical point of view. But sometimes we do things because this is where we're asked to do to ultimately change, you know, have a change in policy. But and sometimes, exactly, you're never going to see the change point because it's going to be averaged across a large population, and there have been studies that have done that. But again, you know, the goal is always to look at the same question from different angles, because remember that you're trying to convince like a crowd that will try to discredit what you do, and so you try to do it from different perspectives. So if they say you need a change point, then you say, okay, I got that. You need this, then you said, I got it. So then ultimately the law passed.
Right.
I agree with you.
The disadvantage of the change point is that it's actually ammunition for the other side, because if we can't get it below 5, well, we might as well not regulate, right?
Right, it's true, but I do think that you know, there is a recognition that you can get up to 5 because is the background.
And Dr. Amizota online, if you want to ask your question.
Thank you so much for a phenomenal presentation. I've been a big fan of your science, but this is my first time seeing your presentation. So I really appreciate your emphasis on asking policy relevant questions. And you sort of alluded to this a few times in your presentation, but can you talk about what kind of steps you or your team take, you know, once an article or body of literature is published, to actually actively engage the EPA in the regulatory repercussions of your work, and you know, maybe also how that has changed depending on who is, you know, in power. So any anecdotes or lessons you can speak to about really moving your amazing policy relevant science, you know, into action.
Yeah, no, thank you. I mean, I think this is something that myself and every scientist around the world that tried to do something positive during the COVID pandemic had to learn pretty fast. So first of all, the environment changed dramatically from the Trump administration to the Biden administration, in terms of that during the Trump administration, any policy relevant paper that would be published, there were some of the press was extremely confrontational and trying to discredit the work. So how do you deal with that? Well, the best way is to, just in terms of nuts and bolts, I basically write talking points on a Google Doc to me and everyone in the team with products in terms of what the messages are, with products on which question will no answer, with products of which question where we address is a lot of uncertainty. So you basically you products and you try to be as as rigorous as you can. I mean, it's an impossible battle because then some of your words are twisted and so on. So, but the good news is that when you publish peer-reviewed top science, the peer-reviewed top science stay regardless of what the Washington Post is going to publish the following day, right? So now with the Biden administration, I think things are very different. And so that require, it's a different level of work. It's really the willingness to engage with the government and literally teach and explain where the science is. And for example, we work very closely with Governor Cory Booker office and their staffer, and we published a paper, I didn't mention, we published a paper in Nature on environmental disparity in PM 2.5, which then led to a bill signed by Cory Booker and Kamala Harris on environmental justice. So we literally spend days and days with their staffer explaining the science, what it means. But then also goes back to what the scientists can do, right? There is so much you can do. You can publish paper, write grants, and spending days in the government. And so it's a balance. It's a balancing act. And I personally, I'm in a stage of my career where I decided I could spend more time into teaching and educating the government agency in policy that I could do when I was an assistant professor. But there is really not, best recipe except time and patience.
You have one more question online.
Hi, thank you so much for an amazing presentation. I had two questions. One kind of direct question about, is the data platform planning is going to be a global data hub or a US only? And my other question is, when we talk about climate and health, the focus inadvertently becomes on kind of adapting to climate disasters like wildfires. However, a lot of focus in the climate space is on, greenhouse gas mitigation. So how can we as environmental health researchers support this discussion on, policy related to climate mitigation more directly, carbon reduction, beyond kind of setting the lower air quality standard, as you said, so things like facility siting and, questions around kind of location of trucking facilities and things like that is what I'm thinking about, but I would love your perspective on that as well.
Yeah, I think I completely agree. So if you think about it, took me 25 years to build the research as a platform and think specifically about air pollution and health, right? And now, what we're doing, and that's why I really value, and I think it's so important to build a consortium, because there is no way a single investigator, a single team, or even a single university can address all of these problems. So if you start with the research as a platform, and that has a base on a lot of data, then you start having other people working on it. So, John, you have, a grant on wildfires and wildfire disaster and Alzheimer, right? So it's looking also at the disaster preparedness. Rob is thinking about adaptation and disaster response in the context of tropical cyclone. So, you try to build the environment that then hopefully accelerate and empower additional people to look at this issue, because this problem is so complex. And all of these problems also, this is the other thing, which why I really believe that research data platform is so important. That all of these questions are highly interconnected. So if you want to think about the health impact of tropical cyclone and health, you don't only need data on tropical cyclone and health, you also need data on temperature, you also need data on wildfires, right? So this is going to be an organic, and I think, in always growing and hopefully finding an environment that accelerates the work of others. That's really my goal. Moving from domestic to global, absolutely, that's the intent. So we are now, I'm working on building a similar research data platform for the country of Madagascar. And the reason came because a colleague of mine was able to get all of the health data from all of the clinics in Madagascar for the last 20 years. And so we are augmenting with remote sensing data on climate change exposure and working with the government. So Madagascar is the next in the list. And then again, I think the idea would be that as you're building and you document the story, the same way when we fit the Cox proportional answer model, first it took, weeks, and then it took 15 minutes. I hope that 25 years it took to build a user platform for air pollution in the US. Hopefully it's going to take 6 months in Madagascar. Maybe it's going to take 1 week, in a different country. And so that's really the intent. And I agree with you. I mean, I think this problem needs and must be studied in the global south as well. And it's important that it's not going to be done in isolation, right? It would be absolutely a shame if someone build a climate and health research data platform in India and it's going to be within a data team, right? Because these could be things that could be studied by hundreds of thousands. But thank you.
I'm afraid that we are over time, so I want to respect everyone's time. We have a busy schedule for our guest today. And thank you, Francesca, for being with us. Phenomenal. And thank you, everyone.
Thank you. Thank you for your question. Thank you.